Hello, ladies and gentlemen. It's Matthew Farrow here, and welcome back to my space. This is an introduction video, or maybe I should say a motivation video for a series of videos where I talk about ways to evaluate limits of functions without using the L'Hopital's rule. So in this video, I will be giving an introduction, a subtle introduction to the concept of limits without going in depth into the theory, because that will require another playlist entirely. And I will also be providing basic tools and techniques that we will need to evaluate limits without the use of this rule. So let's get right into it. So what is limits of a function? So generally, the concept of limits is very vital in the study of calculus. It is the first of the three major topics covered in any typical calculus course, the other two being differentiation and integration. So the limits is very basic and foundational because the differentiation and integration of functions are built upon the concept of limits. In layman terms, in simple terms, the limit of a function describes the behavior of any function as the input value approaches a particular value. It helps us to understand what value, that is, if it exists at all, a function is getting close to. So even if the function is not defined at that specific point. So for instance, if this is a function, 2x minus 2 over x squared plus 1. So if I'm interested to what happens as I get close to x equal to 1, then this limit tells us that value specifically. And although there's a difference between evaluating a function at a point and getting the limit of the function at that point, for most functions, what we just do is to substitute directly and hope we do not hit an abomination. What do I mean? So for this example, so the limit is asked about what happens when x approaches 1. So we just substitute directly. So we do 2 times 1 minus 2 over 1 squared plus 1. So this is 2 minus 2, that is 0 over 2. And that is a legit answer. That brings us to what do we consider as legit limit answer. So we have real numbers, which includes the 0 we got up there. We have any real number, whether rational number or irrational number, whether negative or positive, minus square root of 2, okay, 72 over 158. All these are legit limit answers. Then the next thing is positive infinity or negative infinity. These are valid limit answers. Then not all limits exist. In the other playlist where we will discuss deeply about the concept of limit, the idea, the theory behind limit, we'll look at the sided limit. So when the right limit does not agree with the left limits, we say that the limit does not exist. So DNE actually means does not exist. So does not exist is different from undefined. There is nothing like undefined as a valid answer to a limit question. So that brings us to what happens when we tweak the question a little bit. So in this case, when we have limit 2x minus 2 over x squared minus 1 as x approaches 1. If we try the direct substitution here, we're going to get 2 times 1 minus 2 over 1 minus 1. And in this case, we get 0 over 0. This is not good. This is not good. It is one of what we call the indeterminate forms. There are 7 of them, and this is what I like to call abomination. So we cannot have these abominations when we are dealing with limits. And what are they? We have 0 over 0. Generally in mathematics, any division by 0 is said to be undefined, including 0 over 0. So some people would think 0 over 0 is 0, but no, it is undefined. But in the concept of limits, it is an indeterminate. So we have 0 over 0. We have, so many of the indeterminates come from the combination of 0 and infinity, and I think 1 or 2 of them come from the usage of 1. So 0 over 0, we have infinity over infinity, so which could be plus or minus in either case. Then we have infinity times infinity. We have infinity minus infinity. And we have 0 raised to power 0. We have 0 times infinity. So that is 1, 2, 3, 4, 5, 6. And the last one is going to be 1 raised to power infinity. So all these are indeterminate forms. What does that mean? It means when we substitute directly and get any of these are abomination, then we know we need. So that doesn't mean that is the end. So when we get this, what it only suggests is that we need to do some other stuff. And what are those other stuff? That brings us to the techniques that we make use of. So once direct substitution gives us any of these or something over 0, then we know that we need to try one of these. So if it is simply a rational function, we can try algebraic simplification. We could try factorization. For instance, this particular question here, I could do factorize the numerator to be 2 into bracket x minus 1 and the denominator to be x plus 1 x minus 1 using the difference of 2 squares. So in this case now, x minus 1 cancels x minus 1. We can do this because we are not interested in what happens at 1. Because at 1, that will be saying 0 over 0, which does not make any sense. So because we are only looking at what happens as we approach 1, we are allowed to do the cancellation. So this is the limit as x goes to 1 of 2 over x plus 1. And we can now substitute directly again. That will give us 2 over 1 plus 1, which is 2 over 2, which is equal to 1. So this helps us. So one is algebraic simplification and factorization. Then we could also have rationalization when we have radicals. So if I have x minus 2 plus 3, I could multiply by the conjugate of that, and multiply both the numerator and denominator. So one thing that people get surprised by is that we can rationalize any part of the fraction, either the numerator or the denominator, depending on what we care about. So like I said, I'm not going into too many details about that for now. So the use of conjugates, I purposely separated this because it's a little bit different from rationalization in general. So use of conjugate is what we're going to see most in this playlist, because it could apply also to trigonometric functions. And when we do that, we are not doing rationalizations. For instance, if I have something like the limit of 1 minus sine x over something as x goes to 0 or pi, I could actually, although this is not a problem, because if I substitute directly, this is going to give me 1 minus sine pi over pi, and that is 1 over pi. Sweet. But in a case where we substitute directly and we get one of the indeterminates, then we can find a simplification of this function by multiplying by the conjugate of 1 minus sine x, which is going to be 1 plus sine x over 1 plus sine x. And hopefully things turn out to be nice. Okay. And but you see, some students do not really go through these basic techniques, and they just jump right from direct. In fact, some do not even try direct substitution. They just go straight to the last resort, which is the use of L'Hopital's rule. So again, this video is not one that is meant to talk about the full details and theory behind L'Hopital's rule. But what L'Hopital's rule is saying is that the limit of f of x over g of x as x approaches a particular value is the same thing as the limit as x goes to a of the derivative of f of x over the derivative of g of x. So far, the limit of f of a is equals to g of a equals to 0. So what it means is that if you tried the direct substitution at the beginning, so you get either 0 over 0 or you get infinity over infinity. So this is the L'Hopital's rule, but in most cases, this rule comes after the topic of differentiation has been taught. And teachers, when teaching limits, do not appreciate the use of the L'Hopital's rule because it has not been introduced. So it means for most questions that you would see, that gives 0 over 0, infinity over infinity, one would require some creative ways to maneuver and to be able to get good answers, determinate forms. So the good answers include infinity plus infinity, in addition to these three answers. So infinity plus infinity, we know that it can be determined as infinity. We have infinity times infinity, which is infinity. They are not numbers. I'm saying if one of the functions approaches infinity, the other approaches infinity, and the addition comes, we can add them together and get the infinity, unlike infinity minus infinity. Then we have 0 raised to power infinity. If our limit tends to this, we know the answer is equal to 0. That is not indeterminate. So, and if we have 0 raised to power negative infinity, that will give us infinity. All right, so like I said, when students are introduced to L'Hopital's rule, they forget every other method and just go right into using L'Hopital's rule. Although it makes life easier, but we could always, be smart enough to answer or evaluate limit questions without having to use the L'Hopital's rule. And that is why I'm creating this playlist, for us to see the things that we can do to avoid the use of the L'Hopital's rule. So I'm going to stop the video right here because it's becoming longer than what I would expect. And in the next video, which I'll term the second introduction, we'll look at some tools that we can use to solve some of the questions that we have here without the use of L'Hopital's rule. See you in the next video.